Hello, this is Vasishta from Aerobee section. Today I am going to explain about aircraft structure idealization. Coming to the introduction of concept of idealization of aircraft structure idealization of aircraft. Here, coming to the introduction, an aircraft is a device that is used for indeed to be used for flight in the air. Major categories of aircraft are airplane, rotorcraft, glider, and lighter than air vehicles. Each of these may be further divided further by major distinguishing features of the aircraft, such as airships and balloons. Both are lighter than aircraft but have differentiating features and are operated differently. Coming to the overview of an structural design of an aircraft, coming with an passenger aircraft configured for stability, negative tail lift, pitch stability. Here we can see these are vertical stabilizer, rudder, elevator, horizontal stabilizer, flaps, ailerons, wing tip, fuel tank, slats, engine attachment, landing gear, etc. As we can see, the fuel is into the wings. Coming to the lift loads of an aircraft structure. Lift is generated by producing a higher pressure below the wing than above it. Higher speed airfoils above wing than below streamlines together than above it. Higher speed airflow above wing than below streamlines closer. Here we can see the low pressure with the low pressure at a high the from leading edge to trailing edge of an airfoil. As we can see, we have lower pressure at the upper side of it and higher pressure at down of an airfoil. And coming to the streamlines around an airfoil and pressure distributions around an airfoil also be seen in this diagram. And the resultant force acts acts to the center of pressure, normal to the stream corp varies with an angle of attack. Pitching moment caused by unequal pressure distributions around airfoil. High-speed airfoils above wing, then below streamlines closer together. As we can see in this, lift is generated by producing a higher pressure below the wing and then above it. And the wing structure. Coming to the wing structure, it's a very typical structure as you can see here. The wing has the wing box, a leading edge, trailing edge, and a wing tip and fairings. Coming to wing box, primary wing structure, it consists of total ribs. The ribs are also made up of in the shape of airfoil. And the leading edge, at a fixed leading edge, we have slats, root nose, pylon, engine attachments. And to the trailing edge, we have fixed trailing edge, spoilers, ailerons, flaps. These are the main control surface of an aircraft, which are at the trailing edge of a wing. At the trailing edge, the airfoil is cut into the shape of an ailerons, spoilers, and flaps. And with wing landing gear attachments, or also be in this wing structure. And we have fuel tank inside the structure to save the space and to save the weight of an aircraft. As we can see here, we have digital mock-up for wing box. Upper cover removed with the digital mock-up of wing box and digital mock-up of A350 wing. It's a backside view and it's a front leading edge view and the trailing edge view. As we can see in this wing box, carries the main structural load from the wing and aerodynamic inertial movable fuel. Closed cell structure allowing resistance to the shear torsion and tension loads. Location of fuel tank supporting the landing gear and engine if there are wings mounted. As we can see in this diagram, the wings are attached like this, and inside the wing we have fuel tank and also the structure of an airfoil structures which has been made earlier. This is the shape of a wing. and we have closed cell, and location of tank will be inside this engine mounts and ailerons, flaps, wing load. Coming to the wing loads, wing from finite element model provides that shear moment and torsion. Lift is generated upwards as we know, and bending due to the lift variation across wing, torque due to load offset from center of twist flexure center. Wing complexity. As we can see in this wing complexity of spars. Spars are generally made up of some lighter material which gives supports to the wing, which gives supports to the total wing with the ribs and spars. As you can see, span-wise member that carry shear loads, fuel tank boundaries. As you can see, these are the ribs and the spars are attached inside the ribs. Here we can see the generic wing. Here we have ribs, front spar, center spar, and rear spar. There are three spars inside this generic wing, and rib. A rib is made up of some kind of material and in the shape of an airfoil. And we have spar, which is also made from a lighter material, and the stringers are also inside the wing. Stringers are also fixed inside the wing. And wing complexity of spars. For larger aircraft, the spars are usually made up of multiple sections. Sections are normally joined together with joint plates and straps. Here we can see the web joint plate is also attached to the ribs and spars of an aircraft. Load carry mechanism of spars. As you can see, the wing load, the spars are attached to the wing load so that the rigidity of an wing is also be seen in this picture. Wing complexity of ribs. Ribs play a major role on structure of a wing. As you can see, there are multiple ribs and multiple spars, and the total ribs are attached. The spars are attached to the ribs, so that will get a shape of an airfoil. The wing will get a perfect shape and structural rigidity. As you can see, castellated edges allow the strings to pass through the rib feet to attach to the skin. As you can see, manholes allow access within the wing box and movement of fuel. The ribs contains holes which help us to keep an stringers or the fuel to pass through the wings. And stiffeners and crack stoppers are machined or bolted onto increase the strength of an overall structure. Coming to the wing complexity of a skin and stringers, the skin may be assembled from multiple panels. Joints between skin panels are made at stringer locations and reinforced with butt straps. Stringers prevent skin buckling in compression and aid with bending strength in tension. The tension, fatigue, and damage tolerance. Compression of a top cover. Stringers are riveted into the skin or integrated mesh and formed into the panel. As we can see, these are the stringers which are attached to the skin of a wing. And access holes on the bottom skin allows entry into the wing box for inspection of internal structure and cleaning of fuel tank. These are the holes, or these are the access holes made at the below the wing or below the skin of a wing. The root joint. The root joints are important on attaching ribs and spars to the skin and also to the stringers. As we can see, when the wing attaches to the center wing box in the fuselage, the cruciform and triform fittings are used to attach the upper and lower covers respectively to the center wing box. Patent application number is given. As we can see, upper and lower joint fittings are used to attach the spars. As we can see, these are the spar inside it. In wing structure, we have center box wing fuselage, triform fitting, and cruciform fitting. And the root joint is given to the fuselage, which is also a strong fuselage setting. Wingtip. So as we can see, rigid structure fixed to the end of the wing box. and the structure is built in similar way to the wing box with sparse, rich tinges and skin. Forming the structure contain the navigation and strobe lights. This is the wing tip joint and a wing top tip box, wing tip trailing edge, wing tip edge joint and trailing edge, fence upper, fence lower. This is the wing tip which has been made with stringers, spars, and also with the skin. Wingtip, winglet, and fence. With wingtip, we have illustration of vortices created at the wingtip. When we have wingtip, we'll have less vortex, and when we have conventional wingtip, we'll have more vortex form at the wingtips. A winglet or wing fence can be added to the end of a wingtip to reduce the induced drag effect of wing. A winglet generates more load than a wing fence, but design of the wing and wingtip consider these extra forces. Chocolate in Airbus trade name for the winglets being added to the A320 family. As we can see, this is the vortices formed at a wingtip. As we can see, it is a normal conventional wingtip which has more vortex forming, and the induced drag will also get increased. And we have blended wingtip which reduces induced drag and will have less vortices formations. As we can see in this diagram, we have blended winglet and the conventional wingtip. So this is all my explanation of first concept of idealization of aircraft structure. Thank you.